And this led to a whole line of work trying to relate category theory to quantum mechanics. And in 2004, Samson Abramsky and Bob Kricke wrote a very influential paper showing that a certain quantum process that goes by the name quantum teleportation, and also other quantum processes, could be understood using category theory and using diagrams that resemble Feynman diagrams. But here, the edges in these diagrams, which now I guess we're reading from top to bottom rather than across, the edges are not describing elementary particles, but just states of an arbitrary quantum system. So it could be an electron or it could be some larger system. And I don't want to try to explain this in detail, but these are pictures of morphisms in some category, and they're equal to each other. And these morphisms describe some process where one participant, who always is called Alice in cryptography, communicates a message to another participant, who's called Bob. And in quantum teleportation, you have the superficial appearance that you're communicating faster than light. But in fact, what's really going on is that you've laid the ground for the communication by some classical process that has already transferred some information, and then the rest of the information is transferred on the basis of that. In any event, quantum teleportation was a sort of magical, wonderful thing that you can do in quantum mechanics, and this gave a kind of category theoretic account for how it's working. And that was quite exciting to people because it took the quantum applications of category theory out of the realm of elementary particle physics and into a new realm that was developing, which is quantum information theory or quantum computation, which has the potential for being a quite practical thing. And indeed, already quantum cryptography is used. So on the basis of this and other work, and also on the basis, I should say, of a huge amount of charisma, Bob Kricke and Samson Abramsky built a huge group of people at Oxford, sometimes called the Quantum Group, working on category theory, the foundations of quantum physics, and quantum computation. One interesting thing about this enormous group here is that it's in the computer science department. So not a mathematics department, not even a physics department, but a computer science department. Here's Samson Abramsky here, and here's Bob Kricke looking sort of disreputable over on the edge. That's completely intentional. He's like that. And here are many, many people, including I see Jules Hedges, who was mentioned in the previous talk. He works on categorical cybernetics. So Kricke and co-authors developed this diagrammatic method for explaining quantum physics. And they eventually decided it would be very good to write a textbook on this. And so here's one of two textbooks that Bob Kricke helped write on pictorial methods of understanding quantum physics. And the one interesting thing about this book, so first of all, I recommend this book if you're interested in learning category theory from an unorthodox and sort of easier approach than the conventional one, because it's very pictorial. But I mention it because part of what you wound up doing is hiding the category theory in the sense that you don't run around saying category and functor and all sorts of other jargon like that a lot. Instead, you draw pictures of processes and you explain these pictures in a hands-on way, and you explain how you can stick one picture onto the other, which is composing morphisms, but you don't say the word composing morphisms necessarily because you don't need to. And this is one of a generation, I should say, a new generation of category theory textbooks that are part of the applied category theory movement. So if category theory is going to reach directly to many different communities at different stages of the knowledge chain that I drew at the top of the talk, it means that you can't force people to first become mathematicians before they then start doing things with category theory. The traditional approach to category theory treats category theory as like some finishing school that you engage in after you've already learned abstract algebra and this and that, and algebraic topology and so on. That's just too onerous a path to category theory if you're trying to get computer scientists, much less business people, to get some inkling of category theory. And it's not really necessary to take that elaborate route because category theory is something so fundamental that it can be explained more directly. I especially recommend Eugenia Cheng's book, The Joy of Abstraction, which is a really wonderful introduction to category theory for people who have not had much prior exposure to mathematics at all. And it goes all the way up to the Oneida embedding theorem. So in 2021, Kirka actually left Oxford University and he became the chief scientist of a company called Quantinuum, which uses category theory for quantum computing and also natural language processing. This is a picture of him on the Quantinuum webpage. As you can see, he's trying quite hard not to fall into the stereotypical academic image here. He's a great guy, by the way. You shouldn't mind me teasing him like this. I think, though, that it is important that having people with personalities who are willing to break out of the stereotypical mold of a math professor is important in this whole category theory application movement. I should say that there's a lot of interaction between quantum computing ideas and natural language processing ideas, which I won't really have time to get into. To some extent, they were visible in the last talk, but if you want a real emphasis on the natural language processing aspect, the works of Ty Dene Bradley are very good. She's another newer explainer of category theory. It's a non-category theorist, and she is also working in a company that uses quantum methods and categorical methods for natural language processing. But functorial semantics is extremely general, so it's not just applicable to the topics that I've already mentioned. So in lots of areas of science and engineering, people use a syntax where you draw diagrams and then a semantics where you convert those diagrams into math, which is very often the systems of differential equations. You're describing how things change in time. You're describing dynamical systems. So you use differential equations. But the interesting part is that hooking up diagrams to each other is actually composing morphisms in a category. And the fact that you're working with functorial semantics says that when you compose those morphisms in the syntax category, your functor will map it, the resulting composite, to the composite of the two systems of differential equations that each picture separately is mapped to. So in other words, there's another category lurking around here where the morphisms are actually systems of differential equations. Systems of differential equations with some specified inputs and outputs to serve as the source and target of your morphism. Here are some different pictures. You've seen a bunch of these types of pictures, I hope. So electrical circuit diagrams are one of the earliest and very widely used. This thing here is called a Petri net, and it's a Petri net of a particular model for the AIDS virus and its interaction with blood cells, infection of white blood cells. This here is a very small diagram in the subject of control theory, where you have some process that in an industrial plant that you're trying to keep under control. And so you take feedback, you read off information from that process and you use it to feedback, affect the process itself to keep it on track. I mean, the very simplest example here would be like a thermostat, but in industrial chemistry, they become much more elaborate. And so there's a whole diagrammatic language of control theory that you can read about in textbooks on that subject. And this is a little diagram of some molecules in molecular biology. In molecular biology or biochemistry, they have so many different diagram languages that in fact they've set up a committee to standardize the diagram languages so that people reading different biochemistry papers can look at the diagrams and not have to be explained each time what the diagrams mean. But it's sufficiently baroque that that the committee wound up choosing 3 different diagram languages because they need multiple languages to describe different things they're interested in. So these are very widespread, and the people in these different subjects don't think of what they're doing here as category theory. They don't think of it as mathematics. They think of it as, this is the stuff we draw to understand the differential equations that you can convert these pictures into. The equations are the math, but these pictures are our own private little trick for understanding what's going on. But I claim that these pictures are actually also mathematics. These diagrams are morphisms in various categories, which are using functorial semantics to convert to differential equations. So I decided that had to be true, and I wanted to work out the details around 2012. So I asked Brendan Fong, who eventually became my grad student, to tackle what I thought would be a very good first example, namely electrical circuits, because everybody knows about electrical circuits and the mathematics of them is in some sense very well understood. Linear electrical circuits, for example, made out of just resistors or maybe capacitors and inductors as well. So I asked them to create and study a category having open electrical circuits as morphisms. So these are electrical circuits which have certain things hanging out, which serve as inputs and outputs. I think in the last talk they were called cilia. So these are just these dots here. So he took forever to do it, so it seemed, but it turned out that what he was doing was not just answering the question that I asked, but in fact, answering a much more general question. He invented a general theory, which he called decorated cospans, for handling this problem, but also all the other problems that I described. That is essentially all the other kinds of diagram languages I showed can be understood using the theory of decorated cospans, although the details have to be individually worked out in each case. This decorated cospan formalism is a recipe for getting categories of this general sort. And so naturally, it did take him a while to do a good job of it. And he finished his thesis on it in 2016. I won't attempt to explain decorated cospans any more than I just have. I've given lots of talks on decorated cospans, and you can see on YouTube me giving talks about them if you're interested. I just want to mention one little thing is that, well, first of all, here's Brendan Fong, and here's another student of mine, Blake Pollard, who together with Brendan applied this theory of decorated cospans to the second example that we tackled, which was Markov processes. So Blake did a lot of work on Markov processes. And another thing I want to mention is that Brendan went to get his PhD at Oxford, so he was in the enormous group that I mentioned of Krka and Abramsky, and I believe Krka was his de jure advisor, but in fact I was the de facto advisor talking to Brendan about this problem, and so nonetheless it's really important that this large body of people at Oxford is spreading across the world, doing many things, and Brendan is one of them.